Good morning, everyone. Thank you for coming to the session this morning. I hope you've been having a great conference so far. Today we're going to talk about geospatial analytics with your big data. And I'm going to start right away with why big data and geospatial. Big data has been a big topic. Everybody has been having a great time using the tools and the capabilities and getting the insights to solve many of the new challenges that organizations have been facing, whether it's fraud detection, intelligence, or better decision making. We've been making very good strides in the big data space. However, we haven't really gotten location into this in a very strong way yet. So far, everybody has been collecting a lot of data that's coming from log files or information that's being uploaded to your big data environment, information that is being observed and recorded, social media content, imagery, recordings, other kind of information that's coming from business information. Machines have been generating a lot of information. In fact, that's a lot more information that is human-generated. Tools and capabilities that track where people are, what's happening, events, and of course, enterprise information that's also part of the big data. And if you look at all of this, you will see one thing that's probably common, but has been a little bit missed in the process of evolving big data, and that is location, and how location can play a very big role in what we do. Typically, when we analyze a problem, we as humans, without machines, we typically start thinking with location and time as the context, and then we start analyzing the details within that problem. So location and time have always been a very important aspect of our view of the world. Whenever we view information and data, we take that into account. Big data is now becoming part of the geospatial content that Esri is recognizing for its tools. And what we're trying to build is the capabilities to allow you to incorporate that in your big data environment. So how would geospatial and big data work together? Our purpose is to geo-enable and enrich big data. The dilemma with big data is you move your programs to where your data is, not the other way around. And for analysis, we've typically been doing that paradigm in a reversed way. We always brought the data to where the tools for analysis are. But with big data, we don't want to do that anymore. We want to move the tools to where the data is. So wherever you've collected your data, where the data resides, we want to geo-enable and enrich that data. Then we want to be able to filter and aggregate where the data is, and then bring the results in for visualization where the tools are. So you don't want to move all your big data to the tools. You want the tools to just get the filtered end result, and that's where visualization and extra complex analysis can take place. So what are the questions that geospatial can help answer? I wanted to include a few examples to help you understand what is the value that it can add. We'll take, for example, a space like utilities. Smart meters are collecting billions and billions of readings every day. These readings are coming in a lot of the time. Utility companies are trying to make use of that sometimes. It's too much information. But if we put all of this to use, we could see some critical questions answered, like where are the failures happening? If the smart meters are reporting information about everything that's going on within a neighborhood, you can identify if there is a failure specifically happening at a specific location where maintenance is needed right away. Or you can predict ahead of time where your maintenance plans need to be based on patterns. It can also do better business by understanding, based on the patterns of usage, how to offer better deals or better packages and services in specific areas versus others, and tailor your business to what your people need. Additionally, another area, agriculture. So agriculture is an area that is very rich with data, where analysis and location make huge difference. Tractors today are always powered with control boxes. These control boxes read so much information, and they collect the data based on certain grid structures, and within that grid structure there are hundreds of information that is being collected, whether about the soil or about the nature of the weather in that location. Within a field, there are so many variations, and that information being collected gives farmers a lot of insight into how to get the best yield out of their farm. Also, it gives companies that provide seeds and agricultural tools the best means to provide the tools to the farmers to get the best result. So this is an area, again, where big data, along with geospatial and location, can make a huge difference, answer very complicated questions. Another area that we're all probably more familiar with, and that's smartphones. So smartphones today generate billions of readings as well. These readings come not just from the different activities that are happening as the phone moves around, but the different applications that we're using on the phones. Sometimes the fact that you start an application shows an interest that when you are in this specific location, in this time frame, there is interest to look for a specific type of information. These insights doesn't just help the telcos with the services, but it also helps people who build mobile applications understand how to tailor to their markets and their users' needs. Such insights are also possible through using big data with location and time. Also another area, healthcare. This is an area where the information about the services, health indicators based on so many factors, these are critical questions that affect every one of us. And I got one more example, social media. So I tried to include as many of these examples where location can play a role. And for social media, we don't usually think that location can make a big difference, but in fact, when we include information about what we like, what we don't like, and we are living in a certain area or we are traveling to a certain area, people who provide services will monitor that and they can get back information. Maybe one of their branches isn't doing a good service and they need to address that. Maybe they have an issue that they need to address. Maybe they identify where their brands are most successful if they want to do a trial for a rollout. Understanding how the location plays into all of these factors makes a very big difference in how the services are provided if you have a problem in a specific area versus a problem with everywhere that you need to address. So with these examples addressed, I hope you kind of get a good feel for how big data and location can work together and the value that location can bring in that area. I also want to explain a little bit more about geospatial analysis. If you're not familiar with it already, geospatial analysis is not just about putting a point on the map. So we typically see a lot of maps online and the ability to do mashups, and the end result is, well, you know, we could put the points on the map, and that's visualization for a map, and that's sufficient. But what we're talking about is a little bit more complicated than just putting a point on a map. Geospatial analysis typically, I like to simplify how it is explained as two different things. First, simple operations. So understanding geometry, operations on geometry, and how to do certain capabilities, like if a point intersects with a polygon, and from there you can understand which points fall within which area. Good example for that is if you're trying to find which cell phones fall within a certain zip code at the moment. So that's what a point in polygon query is. Similar examples that has to do with intersections, union, all kind of operations that you can run with geometry on your data, that is the simple operations factor. But then comes a higher level of analysis that includes tools. And that higher level of analysis allows you to automatically get insights out of your data. For example, generate hotspots. Understand where are the hotspots within your data. Not just where the data tends to accumulate, but where there is statistical significance of this accumulation. And identify if it is just random or if there is a pattern to it. And through that, identify these patterns. That kind of capability comes with specific tools that will just ingest the data and generate for you these results. So how does geospatial analysis get implemented with big data? I wanted to go through a few high-level examples and then maybe give you some details about the APIs and show you some demos for that. Right now, typically when you do a query on your big data environment, whether you're using NoSQL or Hadoop, you typically include something, if you're using Hive, you would use Hive query language, and you would include something like a SQL statement down to your data, get back the data. What we're trying to do and what we've offered right now is the capability to do a geospatial query down to your Hadoop environment using Hive. So rather than just saying select from this table these fields and do all the typical SQL statements, you could also do select from cities where near and do a near operation where you can identify based on an X and Y that is being passed, what are the cities that are identified in this table close to this location. You can also do operations like the ones I mentioned where you do a pointing polygon. So you could see in my table cities, all these points, which ones of these is contained within this polygon. So I can identify if there are specific locations that I would like to highlight within my polygon. I could do a subset and extract all these fields based on that. So these are spatial operations. If you've been using RDBMS that has spatial capabilities, you've probably seen these before. But what is new is that now we can run them on top of Hadoop, which was not possible before. So if you have a Hadoop environment, what we offer is a number of libraries. All of them are open source in the GitHub space. The geometry library extends the Hadoop core, and this is how we enable Hadoop to recognize geometry and geometry operations. Through that library, you can write MapReduce applications in Java. But then for analysts who want to write SQL-like statements that include spatial operators, we also include a number of UDFs for Hive. And the Hive spatial UDFs extend Hive to enable analysts to send down to the Hadoop environment all these SQL statements that include the spatial operators, just like the ones I showed you in the previous slides. These are available through a GitHub project called GIS Tools for Hadoop. And that project is based on the Apache license. It supports running your operations for spatial queries, whether you want to do filtering or aggregation or any of the spatial queries that I mentioned. You could use that source to do that. What we're also looking for is integrating this with higher-level tools that will help with visualization capabilities to run maps, and possibly integrate with complicated analysis tools like the spot analysis and the other type of tools equivalent to it. So we've added to the set of libraries an extra library that integrates with our tool environment, which is named ArcGIS. And that set of tools is also in GitHub as part of that project. It's called a set of geoprocessing tools. And geoprocessing for ArcGIS is a framework that allows us to utilize tools that are built in, but also allows everybody to go and customize using Python or Java to build their own tools and extend that geoprocessing framework. So within the visual environment, the tools could be utilized. I want to walk through quickly the GitHub repo so you can get an idea of what I'm talking about. So I'm going to go quickly to the browser. Within that front page, you'll see a reference to all the main different projects within GitHub. So we have GIS tools for Hadoop. That's where the GP tools, as well as a number of samples are available. The Esri geometry API, the spatial framework, and there is information on how to get started. Given we were talking about Hive and the UDFs through the SQL statements, I'll just go quickly here and show you the project, and there's documentation that shows the dependencies. Here's the geometry API, and you can get also full documentation. If I go to the Java doc, it looks just like your typical Java doc documentation. I'm not going to go into details, but just wanted to make a quick walkthrough to show you where to go, what it looks like. Switching back to my slides. I'm pretty sure since it's Friday, you already know about EMR by now. So I wasn't sure when the presentation was scheduled, so I had that slide in there, but I'm pretty sure everybody knows about EMR, all its benefits, so I'm not going to go through that. And all the data stores that EMR already integrates with, whether it's S3. One of its greatest integration that I really like is the integration with S3. So sometimes you don't really want to move all your data into HDFS. You want to keep it in S3 and work on it from there. And that's one of my favorite things about it. But the complete integration through EMR with the other capabilities in Amazon is really a great platform for working with big data. So why would we use Amazon EMR for geospatial analysis? Well, it's a very flexible platform to get started, and then from there, grow large. So if you don't have big data infrastructure, if you come from the GIS side and you don't have big data infrastructure, this is a very quick way for you to deploy a cluster. So you don't have to just run one VM on your development machine. You can actually deploy multiple machines in the cloud, get your queries running, do some analysis and play around, and then when you're done, shut it down. Also, it's hosted and managed by Amazon Web Services, so it makes the level of expertise very, kind of lowers the bar on what is needed to know. I've seen what it takes to deploy Hadoop in your own environment and maintain it versus just using EMR, which kind of takes a lot of the details and the hard work off the plate. It's a data ecosystem also. So if you're already using S3 for your data, this is where you put your log files, whether you put it in S3 or you are pushing it to Glacier. This is a great environment where you have complete integration. So the Hadoop deployment integrates with where your data is. It's just a matter of executing the queries and leaving your data without having to move it around. And we talked earlier about how important it is as you collect these large amounts of data, you don't really move it around. You just want to leave it where it is. So in addition to GIS tools for Hadoop, recently we've put out in GitHub a set of tools that allows our users, as well as everybody else, to utilize EMR. So Amazon Elastic MapReduce could be deployed with the Esri Geometry API, the UDFs for spatial, and then through a set of geoprocessing tools, a certain amount of operations could be run in that environment through the analytical interface. So ArcGIS in this case is a desktop application. It could run in your own environment, or it could run on an EC2 machine that you have in the cloud. It can start sending batch operations to a deployment of EMR to do geospatial analysis. Once EMR is geospatially enabled with these libraries, it can now run these type of operations seamlessly. So from the perspective of an analyst, it's very easy. Through the processing tools, they get an EMR cluster started. They push a certain Hive script to it to run the analysis in batch mode. When the results are ready, they bring it back and visualize it, possibly run some further complicated analysis on that. The complicated analysis I'm referring to includes a set of very sophisticated geoprocessing tools that are very unique to Esri products. So while you'll find a lot of people able to create maps and visualize information, it's this extra capabilities for analysis that makes this tool pretty unique. So I could go a little bit into it, but I don't know if I have enough time. But these set of libraries don't just do statistical analysis, but they also allow you to do very sophisticated geographical operations. So if you include the results you get out of Hadoop with possibly geographic information, you could do things like hillshade analysis, solar heat analysis, and very sophisticated types of operations. And again, like I said earlier, you can customize it using Python or Java within the same environment, so it's extendable and customizable. But also what's important, I'm planning to show you this later, is the ability to chain these tools such that the output of one of them goes into another one as input through this drag and drop environment. And then that model that you create through drag and drop could become an automation that you can schedule for it to kick off at some point. So if you have log files that are being accumulated in S3 and you want to run certain spatial analysis on this set of log files, you can schedule this type of operation, and then you'll be able to kick off this maybe nightly or every week and generate reports accordingly. So the set of GP tools that work with EMR, Amazon Web Services, is also available in GitHub. It's under a repo called GP tools for AWS. And again, just to quickly show you what this repo looks like. So when you go to it, if I can find my mouse again. Sorry about that. So within GitHub, there's a lot of information on how to set up the tools. There's instructions on how to get started, how the tools work. They include how you can get EMR started from within the environment and then running other kind of operations like debugging and how to get access to your machine. There's also a number of samples that are included that have examples of how you could do some geospatial analysis. And I'm going to walk through some of these examples that show you how you can run geospatial analysis using EMR. So these tools were used using the geoprocessing framework on the ArcGIS side. But on the Amazon side, it is leveraging the Boto Python library. So this Python package is really very handy. I should say I spent a little bit of time looking into it, and it's very extensive. I'm not sure how popular it is or how many people are leveraging it, but I was impressed by how extensive it is. Right now, the GP tools are leveraging EMR and S3. So you can do uploads to S3 and downloads from S3. Using Boto, and in that case, Boto does a really good job with doing some parallel processing where it's needed, so it can go and create multiple threads as needed. Also, it has complete support for EMR, so you could start an EMR cluster and fine-tune the properties of that EMR cluster. For example, if you want to make sure it never fails or never shuts down on you during an operation, you could turn all these operations on using the Boto setup. So Boto is also available in GitHub, and again, I just want to show you what this looks like. I always like to open the repo rather than just including screenshots. It's a very extensive library. It includes all sorts of different operations for AWS. So for example, if today the GP tools that we have in GitHub are only working with S3 and EMR, and you want to extend it to leverage other services, you can go and use Boto and our GP tools to go and create your own tools to extend it further. It works really easily by getting started. There's a lot of documentation information about where to go and how to get things started. And for the Elastic MapReduce, they have extensive examples on how you could get a cluster started, how you can connect to it. And through Boto, all the operations that we're doing from the GP tools, that's how they're working. So is everything clear so far? Everybody still with me and following? Anything feels like it doesn't add up? Any questions so far? Yes?
You had a slide of the Esri tool set, but I'm assuming that's still running on the client, right? They're not.
Yes. So the question is, I showed a screenshot of a library of tools. Yes, the tools for advanced analysis are still on the client side. This is an area we're looking at migrating some of them down into the Hadoop environment to extend the geometry capabilities. But today, what is available in GitHub is just the geometry operations. So you could do this type of spatial queries. And then you bring the results to run these extra tools on them if you would like to do that. So we'll bring all of this together, and I want to walk through an example here very quickly. ArcGIS Online is our software as a service platform. And through that environment, we offer a variety of capabilities. There are base maps of the different parts of the world. There are services that help users upload their data and create their own map services, and also some analysis capabilities. So of course, as we provide all these capabilities and services in the cloud, we generate a lot of log files. And I wanted to show you an example today based on the log files that we've accumulated for some of these services. So the services I'm talking about includes one of our base maps. That's the world imagery map. And it's a very sophisticated type of base map that includes mashups from different providers, includes some of the best providers in the world. It's not all our data. And what we would like to know is always, where is the service most viewed? So the big question we try to answer with our log file analysis is where is the most hits? Where are the areas where our users will go to more and zoom down into different levels and try to get more details on? That information helps us a lot with maintaining that service. It helps us understand where to keep our data up to date. It helps us operate our activities around rolling out specific areas at certain times. And it gives us insight into how our services are being used, so we can plan accordingly. So with that said, our reports tend to be very visual, as you imagine. We do maps and geospatial analysis, so we like to see all of that on a very nice map. And we get the load for the specific service that we did the analysis for was about 900 million records for a specific period of a few weeks. And the analysis was run in EMR because if we ran all of these records in the database, it's close to about 1 billion records. And putting all of that in just one report, one query was very hard. Our databases didn't really scale, especially when I show you the kind of operations we're doing. You can imagine things weren't really going very well in the RDBMS environment, and we had to do a lot of operations where we would break up the data into different pieces, run the query on each piece, then the results come back, try to consolidate these results again. It was very painful. So working with the team, we were able to consolidate all of that in just one query. And Hadoop really likes very large data sets. So the larger the data sets, it tends to be a little bit faster. So it took us a much more limited time in comparison to all the operations we were running on the RDBMS to just run this one time on Hadoop. And in the end, we were able to generate the results based on all of these. Now, the architecture that was used for this type of operation was based on having our ArcGIS desktop client running within a machine. So the analysts kept that machine running on their own desktop in their own environment in their office. And the tools, the GP tools for AWS were used to just seamlessly go and start an EMR cluster. So in this case, the analysts I'm talking about are analysts in our content team. They are not familiar with Hadoop. They are not familiar actually with Amazon Cloud very much. And to train them to all those tools would have taken a very long time just to solve that one problem. So using the GP tools for AWS, it was easy for them. It's the same environment they're used to. They started the EMR cluster without having to be experts on Hadoop or Amazon from within ArcGIS desktop. And then they were able to upload a script. In this case, the log files, we've pre-uploaded them to S3. So the data has been sitting in S3. And to give you an idea about the structure of our log files, we've broken them down by a weekly basis because that seemed to make more sense. Whenever we run reports, we typically run them on a weekly basis. The size of these files was well-rounded to about 2 gigabytes, which is the recommended file size for EMR analysis. You don't want to have too many small files. So I heard typically from Amazon, they recommended to us to keep the size between 1 to 2 gigabytes if we wanted to see the best results, especially if we keep our data in S3 rather than move it into HDFS. So leaving our logs in S3, It was partitioned based on dates that had to do with 1 week. And within each of these weeks, we had one log file that was about 2 gigabytes. And that was the structure for the data that we ran the analysis on. Then we had our own scripts and logs and other kind of information, the output results, all of that went into a completely different bucket. And using this structure, it's very simple and was very straightforward. The query results came back on timely basis for the reports. And I want to show you some kind of examples for that. First, the data files, they didn't look like your typical log files. They were CSV files. What we have typically done, or what our content team has typically done, is that they would take the log files and they had their own operations to clean them up before loading them into the database. So they didn't want to break that process. But instead of loading it into the database, they were loading it into Esri. So our starting point were these cleaned up clean-looking CSV files. However, if you want to start from your log files directly, I'm pretty sure you've heard about this in other sessions, the SERDs and how they can parse the log files and generate Hive tables based on that. I also want to mention that we worked with 18 map scales. So if you're familiar with how the maps work, you've probably all seen that, the little tiles that kind of line up beside each other. As you zoom in, you get more tiles. So to pre-prepare these tiles, we always identify specific scales. So when you click on that zoom in and zoom out bar, the map is really switching between different scales. So the maps that are typically offered on the web are ranging around 18 map scales. And these 18 scales were also very important to us because we wanted to know where are the areas that our users are trying to drill down to get more details. And I'm pretty sure we've all had that frustrating moment when you keep zooming in, and then you get this empty tile that says no data. Well, we want to know about that so we can see how we can make the experience better. Maybe you can get more data and apply it here. If there are more people zooming in and they can't find anything, we want to make sure we get that data. So for us, the scale was a very important thing. So these are typically the scales that are provided for each of these world-based maps, and we wanted to have it in our script such that we can consolidate up to a certain level. So the scales coming from the upper part and the lower part consolidate to that one layer that will show us how many requests are coming. And we have different reports that do different things, but for this specific report, that was the operation we were doing. So we had quite a bit of mathematical operations to do that identify the X and Y corresponding to where every tile is, in addition to consolidating the tiles to that specific point. So there could be 4 or 5 tiles at a certain scale corresponding to this X and Y, and so on. So we do quite a bit of mathematics to aggregate the results and generate points equivalent to that. So the work we were doing here is heavy mathematical operations that typically ran on an RDBMS pretty well. We were pretty skeptical if we migrate the script to Hive, will we be able to see the equivalent capabilities, especially with all those mathematical things happening? And now that we have the geometry enabled, would we be able to put all these things together? And I was pleasantly surprised. Everything worked pretty well and very seamlessly. It wasn't actually very difficult. The basic script that we ran in the RDBMS, in that case, we were running it on SQL Server. All the operations, we could find the equivalent in Hive, and the script was easily ported. And then the results came back. We did some playing around with the formatting to make it comma delimited rather than tab delimited. But then pulled out the results from Esri, did a very straightforward visualization based on that. So I want to show you really quickly what all of this looks and feels like. I'm not going to do like a live demo on this because of the time. But I wanted to show you kind of the overall experience for what this feels like. So over here, I have this is the ArcGIS desktop tools. The tools that I have been discussing, all the different tools are available here. They're built into the tool. I also added from GitHub my GIS tools for EMR. And I have a tool called EMR Setup. I have customized the tool in order to have my information about my account, my preferences. So whenever I open it, I just specify where I want everything to run. And with one click, I will start an EMR cluster in the cloud from within this environment. So it usually takes about 5 to 6 minutes to start the cluster. So I've run that beforehand. And these are kind of the messages that tend to show up. So in this case, it took about 4 minutes, 52 seconds. And the output of this result is the DNS name and the job flow ID. Now, the job flow ID, if you've used EMR, is very important because that is the identifier for your cluster. If you have multiple clusters running at the same time, that is how you assign a certain job to a certain cluster versus another. So I use this job flow ID to run a Hive query. So this is what this tool looks like. It takes the job flow ID, specifies the region, and then I supply an S3 path to my Hive query. So over here, I've already run that, and this is what the messages looked like while it was executing. In this case, it took about 11 minutes to execute this, and I'm not running all the hundreds, close to a billion record query in 11 minutes. It typically actually takes about 2.5 hours, but in 11 minutes, I'm running it on a sample of about 40,000 records. And I got my result back, and then I used the tool S3 download that's available here. This tool allows me to drill down into the buckets and identify which files I would like to download and download them directly to my local disk. So I have done that already. I've downloaded it. And over here, it took about 40 seconds to download that output file that I generated. I downloaded the file here, so let me show you what it looks like if I add this. So over here already, I have what I call a base map. This is a base map of the US. So let me zoom out a little bit. And it's one of the base maps that are coming from the ArcGIS Online platform. I hope my internet is still working. What I will do is within that table of contents, I'm going to drag my output file that I just downloaded from Hadoop. And this file, part of the structure that I specified in my script is to include the X and Y. So these are the fields that represent that. Also, I have a preset up here to identify a specific geodesic system. In this case, it's Web Mercator, because these points were calculated based on my tiles. So if you've done GIS, you will understand that geodesic systems make a huge difference. That's another thing that's really powerful about this tool is the accuracy and the quality of the information you do when you're doing your geospatial analysis. So over here, I can identify my geodesic system for this X and Ys. And then I am able to view right away. I didn't really have to do any intermediate steps. That was the output file from Hadoop directly into my tool for visualization. Now, this area here is for California. And as you see, the points are on top of each other. I'm not really able to get insightful information about how many hits are happening. So I'm going to take into account some extra fields that has to do with understanding how many hits, the actual hits that are coming in that location. And for this, I have two options. I can use graduated simple. So in this case, here's my field that aggregates the number of hits. I can specify, well, this is how I want to show it. So this will graduate the range based on the numbers. And this is generated automatically. The tool will recognize what values I have in my layer and will break them down for me. Or I could also use proportional symbols. So if I specify my field here, I will start, this is the smallest one, this is the biggest one. So in this case, I will have many values in between. And I could specify the symbols to display in the legend and how possibly to normalize these values if I would like to apply more fine-tuning. But in this case, this is what I would like to show. I can also specify what color I would like this to look like. So if I go back to my graduated symbols, this will look blue. I can pick other colors or pick other symbols. I'll go with blue. And over here, if I zoom in again, you'll be able to see that in the New York area, I can get a little bit more information here about the areas where there is actually a lot more interest. And as I zoom in, I get to see more information about that. Now, I wanted to quickly show you a map that we have pre-generated. So this is the map that we generated, and this is within the ArcGIS Online environment that I was talking about earlier. So this is the actual map generated from the report that I talked about. You could see in it not just the areas in New York are more popular, but all the urban areas tend to be a little bit more popular. And one of the benefits of doing this visualization that came as a kind of an interesting aspect was, in addition to understanding where the demand is, we could also see across the ocean where people are starting to collect our data. So this is where people would start downloading your data, and of course they're not supposed to do that. And this was really a very good way for us to detect what's happening, where it's coming from, and who's doing it, and start to block them as they start to violate our data licensing and download the data locally. So it didn't just help us with insights into who's using our data and how, but also with fraud detection, so we could stop it as needed. So all these kind of scrapping colors you see here are people trying to download the data and where it's coming from. So going back here, this is the base map over here. I can modify this base map. This is the service that I'm talking about that we collected the request for. It's the satellite imagery, and that is the kind of report we are able to use. So for that same exact service, the satellite imagery, we've collected all the usage, and we are able to show who is coming from where. And this was all done very easily, very quickly in the EMR environment, which was something that used to take a lot of effort and a lot of work in the past. So I want to quickly also show you the script. Sorry, I'm jumping. This is what the Hive script looks like. I hope you're able to see this. So in the Hive script, we started by adding a number of jar files. These are the jar files that I talked about earlier that you can get from GitHub. Additionally, I'm creating a function for points. So Hive could recognize our UDF and start identifying points and creating points. And then we also have the table that we want to create. And I strongly recommend, you probably heard that in other sessions, but strongly recommend do not forget the word external when you're creating a table. That was a very easy way to delete gigabytes and gigabytes of data in S3. And of course, everybody was very surprised, like, where's our data? S3 is very reliable. No way S3 could have lost our data. We didn't realize we were the ones deleting the data by saying drop table and then not identifying that our table is external. So that would be a very strong lesson learned. And then here are all the mathematical operations that I was talking about, where we were doing the consolidation. And then from there, we are creating the points that are equivalent to those tiles. So all of that is on GitHub. You're very welcome to take it. If any of our users that publish their own tile files is here and they want to kind of do the same operations, that is exactly the same script we ran on our ArcGIS Online services. So you could take that and run it on your own log files if you want. And in the end, we're creating the heat map final output. This is the actual file that is being written to S3 and that is being collected directly into the tool for visualization. That is the script. And that is the same exact script that ran in SQL Server. And we ported it to Hive, and it worked very well. There were no issues or surprises there. Now, within the sample, for those who would like to play around with this, there is a sample data set that has been partitioned with the same approach. It's about 40,000 records. It's not very large. That's what takes about 11 minutes to run. But if you're trying to kind of get started, this is a good way to get started. If you don't have ArcGIS desktop, you can download the trial version. There's a link for that over here. And you can get that link, download ArcGIS Desktop. If you already have an Amazon account, it would be a very easy way to get started. Download the trial version, use this sample, play around with it really quickly, and see if that generates the kind of reports you would like to do. And one final thing I wanted to show you before I kind of switch back to the slides is the ability to do this drag and drop model builder. So these tools that I have here, I can actually drag them up and specify, here is my Hive query, here is my Esri download. I can drag them all in and maybe upload as well at the beginning before I do anything. And then I could easily specify what I would like to, the relationship between these tools, like the inputs coming in and out. So I could specify the job flow ID coming out from my EMR setup is actually input for my run Hive script. And this means that in this flow, when my EMR setup tool executes and is done, it's going to generate a job flow ID. I will use that for the execution of my run Hive query. And then over here, I can make a variable from a parameter, like a specific parameter. In this case, that would be my path to S3. And this path from S3 would be identified, and I could set a value for that. So I can provide the path to S3 for my query, and this is the query for the type of script we were looking at that we would execute. So the nice thing about a model like that is that using it, you could create your own models, and then these models would be automations that would execute. So for an analyst who would like to be able to execute these automations on a nightly basis, they would create this model, input the parameters they need, and it would easily execute on a nightly basis to go and create the visualizations needed. So going back to the slides, again, I wanted to highlight our lessons learned. External tables are very important. Cluster shutdown protection is also another important thing we've learned. It's something that if you are not sure about your Hive syntax and what you're using with EMR, it would be really good for you to turn that on. Otherwise, every time you are trying to execute an operation and the Hive statement isn't particularly correct, it will terminate the whole cluster and you'll have to start all over again. Cluster sizes for execution time. There's been a lot of recommendations about that in other sessions, so I'm not going to go into it in detail. That kind of typically applies the same thing. I haven't seen a lot of differences when we switch to a little bit of a bigger cluster when it comes to time and analysis. It comes along to creating more cluster sizes based on your number of mappers and reducers that you have enabled. These are the kind of significant things that will show you optimization for the time and performance. I know they've gone through these details in other sessions, so I'm not going to talk about it a lot. But the point that I wanted to highlight is the cost. And cost is a very important thing, especially if we're running operations like this. The way we have broken down the cost is per report. So because the way the tools execute, we start an EMR cluster, we execute the report in a certain number of hours, and then we get the result, we terminate the cluster. So for us, the cost was based on the execution time of that report, and that was the cost to generate that report. So we kind of identified different reports that are needed and the cost to run each one of them, and compared that to the cost of running it in-house on our RDBMS with the time that the DBA has to spend trying to do things. And we've actually found that it's very compelling to move the reports to EMR. So for example, it takes about 2.5 hours to execute a report like the one I just showed you. And that report takes about, on regular basis, it costs us overall something that is less than $100. So in the scheme of things, if we were looking at setting up our own cluster, our own setup, $100, I mean, that's nowhere near to just buying a machine, not to mention setting up your Hadoop, and the people have to be experts on maintaining it and making sure your data is well loaded and running there all the time versus just putting it in S3. The cost comparison was actually very sobering to kind of learn that just with a few $100s, it all works well. And also, for daily operations, we have different members of the team starting clusters during the day, running operations, but we make sure to terminate them at the end of the day. At the end of the month, our bill typically goes about $400, $500 just for being aware of turning off the cluster when you're done with your analysis. So the cost comparison has been really compelling to continue to leverage this for our reports. So in summary, to kind of wrap this up, there is a lot of value in asking spatial questions when you're working with big data. And Hadoop is now spatially enabled. Don't forget to look at our GIS tools for Hadoop and see how you can enable Hadoop to recognize geometry and geometry operations. And we've been using Boto for EMR, and we've used that to build a number of GP tools. The value of these GP tools is that analysts who don't want to learn about Hadoop, don't want to learn a lot about the Amazon Cloud and its intricate details of how it works, these tools will work for them seamlessly within the environment that they could do analysis for GIS in. And showed you a real-world example. I hope the lessons we learned have been of use to you as well. And with that said, that kind of concludes what I had prepared to say, and I'd be very happy to listen to your questions. Thank you.